Okay. Okay, welcome everyone. So the second talk this season will be by Joseph Macula and from the University of Colorado Boulder. And he will be talking about extending class group action attacks via sesquilinear pairings. So Joseph, the floor is yours.
Thanks very much, Maria, and thanks to both you and Jonathan for inviting me to give this talk. So good morning as well, or good evening to everyone else here, and thank you for attending. As Maria said, I'm going to talk a little bit about a recent joint work with my advisor, Kate Stange, about class group action attacks and extensions of some recent results via sesquilinear pairings. So just a quick overview of where we'll go during the talk. I want to start by introducing some prior results by way of giving some motivation for what we've done in our work. Then I'll talk a little bit about the construction of the sesquilinear pairings. I will leave some of the details of exactly how those pairings are constructed to the recent paper of Kate's. You can find a preprint on the archive, and I'll talk more about that when I get to this section. But we'll at least see how these pairings are constructed and some of the fundamental properties that they have. I'll then return to questions of application and talk a little bit about how we've managed to extend the scope of some recent prior attacks. And if there's any time remaining, I'll also discuss some of our work in exploring modular isogeny problems and a couple of results from our paper where we managed to improve on some recent reductions between various types of modular isogeny problems. So I want to talk first about the vectorization problem. So we'll suppose that we have a supersingular elliptic curve, E, over a finite field F. And for the remainder of this talk, when you see F, that's just a finite field of characteristic P, but not necessarily FP, right? It could be FP squared or FP to the fourth or whatever. K is an imaginary quadratic field, and O is some order in K, not necessarily maximal. So a K orientation, as I'm sure many of you are already familiar, is just an embedding of K into the endomorphism algebra of this elliptic curve E, which we know is the quaternion algebra over Q that's ramified at P in infinity. And in particular, if this orientation is such that it embeds the identified order O into the endomorphism ring, then we say that this embedding iota is an O orientation. And in particular, if O is maximal with respect to this embedding, i.e. if it's the largest imaginary quadratic order that iota embeds into the endomorphism ring of E, then we say that iota, this particular embedding, is a primitive O orientation. And in general, we denote a supersingular curve, E, together with a K orientation, just by the ordered tuple. So we can consider the collection of oriented supersingular curves E that in particular are primitively oriented with respect to a particular imaginary quadratic order O. And then we can further consider that set up to a notion of equivalence, which will be as follows. So we consider E iota and E prime iota prime to be equivalent if we have an isomorphism of the underlying curves that also plays nicely with the respective orientations, i.e. It commutes in a sense with these two orientations. Oftentimes in the literature, you'll see this condition written just slightly differently. You'll compose on the right by the dual of phi and then offer a correction factor dividing by the degree, but these two notions are equivalent. So we can then define an action of the class group of O on this collection of primitively O-oriented supersingular elliptic curves. So first we define a finite subgroup of E frac A, just by taking the intersection of the kernels of all isogenies we obtain by considering the embedding of elements of this ideal into the endomorphism ring. And given the correspondence between kernels and, between finite subgroups and isogenies via identifying those finite subgroups with kernels, we end up with a k-oriented isogeny, which we would denote by phi sub frac A with kernel E frac A. And we can then define an action of the class group on the set of primitively O-oriented supersingular elliptic curves as follows. We just take the quotient of the elliptic curve by this finite subgroup, and we define the following orientation, iota sub frac A, to be the one that is just by definition going to commute with the initial orientation iota that we were given together with E. So in general, this class group action turns out to be free. It's not always transitive, but at worst, there are two orbits. And if you want details of this, you can see Onuki's paper about orienting supersingular elliptic curves. You can also consult the paper of Arpin, Chen, Lauder, Scheidler, Stang, and Tran, Orientations in Cycles from 2024. So given our definitions so far, we can actually define the vectorization problem. So suppose we have some fixed orbit in the set of primitively O-oriented supersingular elliptic curves, and we have two elements in that particular fixed orbit X. The problem is to find the corresponding element of the class group of O such that the action of that element on E iota gives us E prime iota prime. So vectorization problems do show up in the wild. For example, the underlying hard problem in Seaside is the vectorization problem. So switching gears for just a moment to talking about a slightly different protocol. We all know at this point, I'm sure, that SIDH is no longer secure. This has been shown by Castryck and Decroux, by Robert, by Mayno and Martindale, and by Mayno, Martindale, Panny, Pope, and Wesolowski. So the upshot of all of this work is more or less the follows. If we have a given secret isogeny, phi going from E to E prime, as soon as we know the degree of that isogeny and the action of that isogeny on the M torsion of the elliptic curve for some M that is reasonably smooth and where the square of M is strictly greater than 4 times the degree, we know phi. And for the purposes of this talk, and I know that there are some differences depending on the context and what people want knowing phi to mean, I just mean we can efficiently compute the action of phi on a point of the elliptic curve E. So recent work of Castryck, Houben, Merz, Mula, Van Buuren, and Vercauteren from 2023, weak instances of Seaside, asks the following question, which is, can we bridge the gap between this SIDH attack to the vectorization problem? Can we find something that allows us to sort of fill in that gap and allow us to, in a sense, transport the SIDH attack over to protocols such as Seaside, where the underlying hard problem is the vectorization problem? So I want to share with you an instructive example from their paper that motivates much of the work that they do. So let's just assume that we have two supersingular elliptic curves defined over FP, and that they are both primitively oriented by Z adjoin square root minus P. We'll assume that the secret isogeny phi is FP rational, and that its kernel is corresponding to the kernel of frac A. We'll assume that the degree of the secret isogeny is known, just assign it D. And in general, we know that if we can recover phi, we can efficiently recover the corresponding element of the class group. So we can say in a sense that the problem reduces to trying to determine phi. If we take M to be a power of a small prime that's co-prime to the degree of the isogeny, and such that this prime splits in the relevant imaginary quadratic field, then we know that we have bases for the M torsion on E and E prime such that we have the following relationships. We know that mapping a P under phi sends us to some multiple of P prime, and similarly for Q and Q prime. In other words, we know that because this isogeny is FP rational, it commutes with Frobenius. Because this prime splits, we have bases consisting of eigenvectors, and so we get this relationship. Now, one might hope to try to use something like the Weil pairing, given all of its nice properties, to try to solve for lambda and mu. Indeed, basic properties of the classical M-Weil pairing imply that the following equation holds. And given our assumptions on M, we can assume that taking discrete logs is efficient. But unfortunately, the Weil pairing is degenerate when we try to pair a point with itself. So we're not going to get any information. However, this example does raise the question of whether or not one could find non-degenerate pairings. In particular, could one define pairings on cyclic subgroups of the elliptic curve that were non-degenerate and were compatible with oriented isogenies in a useful way? And what we mean by compatible will become clear in a moment. So in their paper, in the paper of Castryck, Houben, Merz, Mula, Van Buuren, and Vercauteren, they do manage to construct some examples of non-degenerate cyclic pairings that are compatible with oriented isogenies. And they managed to use these pairings to come up with efficient attacks on the vectorization problem, subject to some conditions. The degree of the secret isogeny needs to be known. The discriminant necessary computations, they needed to at times significantly extend the base field in which the computations were taking place. I should note that some work in preparation does appear to remove condition 2. This is work that was presented at ANTS 16, and I believe at an earlier conference in Europe in April this year. I don't know if the authors have settled on a final title, but the talks have been titled something along the lines of isogeny interpolation. Okay, so I want to switch gears now and talk a bit about the sesquilinear pairings, introduce them, and then, as I said earlier, return to talking about how these pairings can pertain to these class group action attacks. So you can formally define these pairings even on curves that do not have CM. However, for the purposes of this talk, we will always assume that our underlying, in fact, we might as well assume that the curves we're talking about are supersingular. So to begin with the construction, Z adjoint tau, and we can take rho to be the left representation of this order acting on our basis 1 in tau for our order. This matrix implies that alpha acting on tau gives us B plus D tau. We'll also define an action of the order on the Cartesian square field as follows, acting by alpha um, um, a, a matrix representation of. So if we take then rational torsion point, the motion again, we and one can check that indeed these are principal divisors. Also defining factor, right? The function points to one in DQ are for every possible. Because finding the pairing by taking the following of functions So this definition maybe not super illuminated. I haven't taken a look at Kate's and preprint, but what I want to you is that it actually be a fairly extension if you're familiar evaluating a function at. So in a sense, new function divisor, the function in question O, and so too does divisor. If we're interested in details, like that you take a look at Kate's. So is the pairing small, straightforward extension of results of Lenstra. And it's the following. So if we have a curve defined over some finite field F, we have some imaginary quadratic field K, and in order O, such that E is O-oriented. If we take F to be what we call in our paper, the relative conductor of O, meaning the index of O inside the primitive order of the orientation, then we know that the M torsion of E is cyclic as an O module if and only if M is coprime to this relative conductor F. So this tells us in particular that there will be many cases where the M torsion on an elliptic curve is cyclic as an O module, where O is a relevant O orientation.
May I ask what do you mean by cyclic module?
What I mean by cyclic module is that you have an order M point on E, such that if you act by this O module on P, you can obtain all of the M torsion points.
Oh. Thanks.
Yep. So we have many cases where the sesquilinear pairing is non-degenerate, and this in turn also yields some non-degenerate self-pairings. So this previous result here is telling us that, okay, if I apply sesquilinear pairing, I can get some non-degenerate pairings. But what if I want to apply the pairing to a point end itself? Can I still guarantee that I will have non-degeneracy? And the answer is yes. So if we take our previous hypotheses, we have some elliptic curve, it's over some finite field, it's oriented by some imaginary quadratic order. If we add to those conditions, M being actually co-primed to the discriminant of the order, so not merely to the relative conductor, but to the discriminant, and we take some point P that is of order M, then we can come up with this relationship here on the multiplicative order of that self-pairing, where S is the maximal divisor of M, such that acting on P by elements of O will give us at least all of the S torsion. So the difference here is we're only requiring that P have order M, not necessarily that P be an O module generator. However, one can conclude right away that if P is in fact an O module generator for the M torsion, then this self-pairing has order M. And if P turns out to be an eigenvector, then the self-pairing will be trivial. I should note, as an aside for anyone who's read the recent work of Castryck, Houben, Merz, Mula, Buuren, and Vercauteren, that this last result here about triviality of the self-pairing in the case where P is an eigenvector, that is anticipated by one of their results. So it's a good thing, right? We would be very concerned if this wasn't lining up with that. I wanted to just provide a quick little sketch of this proof. So we know that properties of the sesquilinear pairing and assumptions on S give us this following relationship, which tells us in particular that the norm of any element lambda in our imaginary quadratic order is a square modulo the order of the self-pairing of S times P with itself. However, our assumption of coprimality with the discriminant implies then that the order is actually at most 2 times S squared. So that gives us 1/2 of our statement here. And conversely, if I take T to be M divided by S, I can obtain, again, via our assumptions and properties of the pairing, that for some point Q, such that the sesquilinear pairing of P with Q has full order, again, we know this because the pairing is non-degenerate, that pairing raised to the T is in fact the self-pairing of P raised to TA plus B lambda. But what this tells us then is that the self-pairing of P has order at least S. So that concludes the proof. Okay, so that was a statement of non-degeneracy in the case where M is coprime to the discriminant. But in fact, even when M divides the discriminant, the sesquilinear pairing does remain non-degenerate so long as M doesn't divide the relative conductor. And one can see this by unwinding somewhat our original definition of the self-pairing. So it turns out, once you go through some of the formal work, that one can actually compute the M sesquilinear pairing as follows. It's really, in a sense, a product of a bunch of Tate-Lichtenbaum pairings, raised in certain cases perhaps to the norm of tau or to the trace of tau, and in certain cases with the point P being acted on by some element of the order. But in particular, if we choose tau to be a nice element of our order, say F times the fundamental square root of the fundamental discriminant, then we know that non-degeneracy just follows from non-degeneracy of the Tate-Lichtenbaum pairing. Okay, so we're going to switch gears now for the second time and move towards talking about some applications. I want to start, though, with some computational assumptions. So from here on out, whenever we say efficient, what we mean is polynomial in the size of the input. So polynomial in log m, and where m is the torsion, and log q, where q is the cardinality of the base field where the m torsion is fully rational. When we say that a curve is O-oriented, what we mean is we have an explicit orientation. So if I were to take some alpha in that order, I can compute its action on a point P on the elliptic curve efficiently. The degree of any hidden isogeny is always known. And finally, we have some nice assumptions on M. It'll always be co-prime to the characteristic of F. It will be smooth, meaning that its factors are polynomial in size. This will allow us to assume that discrete logarithms are computable in polynomial time. And we also assume that we can efficiently write any element of the M torsion in terms of a given basis. So any theorem statements from here on out, we can assume that all of these assumptions are baked in. So to begin talking about extending prior attacks, we'll make a slight modification of our sesquilinear pairing. We'll just define T prime sub m of points P and Q to just be this tuple of Tate-Lichtenbaum pairings with a slight modification in the first argument, where with that pairing we act on the point P by tau. So this pairing remains non-degenerate as long as the M torsion is cyclic as an O module. It also remains bilinear, and it remains compatible with O-oriented isogenies. And what this gives us is the following result. So we have our secret isogeny of degree D, M dividing the discriminant, but co-prime to the degree of the isogeny, and chosen so that, and this is crucial, there are only polynomially many square roots of 1 mod m. If we take P and P prime to be respective O module generators of the M torsion on E and on E prime, then we can say that there is an efficiently computable point Q on the M torsion, in the M torsion, that's of order M, such that a subset of the M torsion on E prime is of polynomial size and contains the image of Q under phi, and furthermore that this collection of points of polynomial size can be computed in polynomially many operations in the field of definition for the M torsion of E. So if we know the image of Q for some order M point Q, then it turns out that the O module structure of the M torsion and phi being an O-oriented isogeny give us full knowledge of the action of phi on the M torsion. Again, right, when we say O-oriented, we mean that the action by elements of O on points P on E can be efficiently computed. So if we have M being a smooth square greater than 4 times the degree of phi, then we can reduce to the SIDH attack. Again, I will mention that work in preparation, as far as I know, still tentatively called isogeny interpolation. It does seem to remove the restriction that M be a square. And by exploiting the O module structure of the M torsion, we are then able to perform all of our computations over the field of definition of the M torsion instead of the field of definition of the M squared torsion, which is what previous work of Castryck, Houben, Merz, Mula, Van Buuren, and Vercauteren are sometimes required to do. So this will give us a new polynomial time attacks on additional instances of the vectorization problem. So the previous theorem is a little bit of a mouthful, and I wanted to talk just briefly about how one might go about proving it. First, you can show that there's some nice elements in our order O. Particularly, there's some element tau that has these following properties. The properties of our modified sesquilinear pairing still allow us to determine the following equation. In other words, we know that norm of lambda is congruent mod the order of this self-pairing to the degree of the isogeny. And furthermore, we're able to conclude from these first two bullet points that if we write lambda as a plus b tau modulo m, that the norm of lambda is a square mod m prime. And I should say this really should read mod m. In general, in our proof, we have to break down into just a couple of cases, depending on the two-adic valuation of m. This sketch is just in the case that m is odd because it's the easiest to state, but it's not required for the statement of the theorem that m be odd. So if we know that the norm of lambda is congruent to a squared mod m, then we're able to conclude that the image of tau p under phi is actually equal to a times tau p prime for some integer a. And given our assumptions on m, namely that there are only polynomially many square roots of 1, we know that there's a polynomial size set of candidate integers a. And furthermore, that these candidate values for a are efficiently computable. So then I should say we have all of our points, and basically what one can do is one can try each candidate value a, carry out the SIDH attack, and see if we have correctly recovered the isogeny. So I wanted to share an example which Kate and I adapted through some correspondence with Father Castryck that illustrates how we can get new polynomial-time instances of the vectorization attack, of new polynomial-time instances of attacking the class group action problem. So if we take the following elliptic curve given to us as a Weierstrass equation of the form y squared equals x cubed plus x, and we take p to be a prime, particularly of this form, so that it's congruent to 3 mod 4, we know that our curve, which has J invariant 1728, is supersingular. And denoting the Frobenius endomorphism by pi sub p, and noting that multiplication by I is given by this following map, then we can define an element tau to be, which we know to be in the endomorphism ring of our curve, as just I plus Frobenius divided by 2. One can check that the norm of tau is indeed 3 to the r and that its trace is 0. If we then take the imaginary quadratic order z adjoin tau, then we know that the norm of tau will divide the discriminant. Taking m to be 3 to the r, that tells us then that m divides the discriminant. And one can check that the fp squared rational points of E turn out to be the torsion of multiplication by p plus 1. This then tells us that the 3 to the r torsion is fp squared rational. So as long as m is greater than 4 times the degree of a secret isogeny, we can carry out the previous attack via computations that take place in the fp squared rational points of E. So this is in contrast to a previous work where a base change to the field of definition of the 3 to the 2r torsion points is required. And this degree grows exponentially with r. So recall our assumptions on what we mean by polynomial runtime. So we have then exhibited some cases where we can get new polynomial time attacks on the vectorization problem. Okay, I have some time left, so I'll talk a little bit about some of the work done in our paper on modular isogeny problems. So this is a slight shift of gears, but hopefully still of interest to some of you. So if we take an elliptic curve E over a finite field of characteristic P, and we take some positive integer that's coprime to P, we can define a subgroup of GL2 Z mod M, just gamma, and we say that a gamma level structure of level M on our elliptic curve is a gamma orbit of a given basis of the M torsion. Then we can talk about isogenies that respect given level structure. So if we have curves E and E prime, both with gamma level structures of level M, we say that an isogeny phi from E to E prime respects the level structure if phi maps the specified gamma orbit for the M torsion on E to the specified gamma orbit for the M torsion on E prime. And it turns out that this framework is very useful for thinking about isogeny-based protocols because many of them are instances of a modular isogeny problem. So essentially, they are versions of the following general problem. Given some isogeny from E to E prime that respects a known gamma level structure of level M, try to determine that isogeny. So we have a couple of examples I want to talk about of modular isogeny problems. The first is SIDH. In SIDH, gamma is just the identity. So the modular isogeny problem is you know the image of your secret isogeny on a basis for the M torsion, and you're asked to find phi. And again, we know that if certain conditions on M hold, and if the degree of the isogeny is known, we can efficiently solve this particular modular isogeny problem. There's a variant denoted SIDH sub 1, where we take gamma to be the following. I should have, sorry, subset, bracket notation here. We're taking the collection of all elements of GL2 Z mod MZ of this form. And what that tells us is that we know the image of phi on a single basis point. So if you know how phi acts on a single basis point for the M torsion, can you find the isogeny? And finally, diagonal SIDH, a third example. And here, essentially what is known is the image of two order M subgroups, cyclic order M subgroups, where P and Q are a basis for the M torsion. So if you know the image of these two subgroups, can you actually recover the isogeny? So recent work of DeFeo, Fouotsa, and Panny from earlier this year categorizes many current isogeny-based protocols by the level structure that's either implicit or explicit. If any of you are interested in, as I'm sure you are, in isogeny-based problems, I highly recommend taking a look at this paper. It's really a nice read, and it's a very clarifying read. So they managed to establish several reductions between various modular isogeny problems. Among those, the following reduction. So if the degree of a secret isogeny is known, and M is some integer that has a large smooth square factor, then they can reduce the modular isogeny problem of SIDH sub 1 of level M to the modular isogeny problem SIDH of level O of root M. So we managed in our paper to improve somewhat on this result. So if we have two O-oriented supersingular elliptic curves over the algebraic closure of FP, and we assume that we can efficiently compute the action of these endomorphisms, again, as long as M is coprime to the discriminant, we'll have that the M torsion is a cyclic O module. If we assume further that the isogeny has known degree and is compatible with our orientations, we can reduce the problem of SIDH sub 1 of level M to the SIDH problem of level M. So there's no loss in level, in other words. We also were able to come up with the following result. If we have two oriented elliptic curves, and we take M to be strictly greater than 4 times the degree of the isogeny, further assume that M has only polynomially many square roots of 1, then diagonal SIDH with known degree for an oriented isogeny is also solvable in polynomial time, so long as either a P is an O modular generator for the M torsion, or Q is an O modular generator, where P and Q are some given basis for the M torsion. This maybe at first suggests that results like, or excuse me, protocols like Festa may not be secure. Again, if you've had a look at the work of DeFeo, Fouotsa, and Panny, you can see that Festa, for example, is an instance of diagonal SIDH. However, this assumption that M have polynomially many square roots of 1 is a key assumption for this theorem. I mean, perhaps the essential assumption, and it's not an assumption that is respected by implementations of Festa. So you could boil down this theorem to, in a sense, saying that if you have an O orientation on both elliptic curves, then you could efficiently solve SIDH in certain cases. But those cases don't actually seem to hold in practice. All right, well, I wanted to thank you all for attending, and I'm happy to answer any questions you might have.
Thank you very much, Joseph, for an excellent talk. As usual, you can just unmute or type in the chat. Yes, applause. If you have any questions, please just unmute or type in the chat. And yeah, I actually had a question too. So like in all of these works, like the degree is assumed to be known. But like, of course, like in a typical seaside or vectorization type of thing, you wouldn't have the degree known, but can it still like reduce the security somehow based on the number of choices of degrees, or would that?
I mean, I suppose that if you knew something about potentially what the degree was, right? Maybe you could try something like, well, I'm going to try to carry out these attacks for every candidate degree, but even then,
there would be a lot of choices, I guess.
There could be a lot of choices, yeah. So really, I mean, I think one takeaway from our work and from previous recent work that I mentioned is that if you can come up with a protocol where the degree is not known, you should.
Okay, right, yeah. Okay, thanks.
If there are any like generalization possibility to like Jacobian curves in, for example, genus 2 curve, you take that abelian variety, whether you can expect some similar result holds. I mean, whether there are some. I mean, okay, I'm actually very new to cryptography, but I'm not entirely sure what is really going on with like if you replace the super singular curve to super special, like two-dimensional abelian variety, what will happen?
That's a great question. Honestly, I'm not sure exactly what would happen. I mean, you'd first of all, right, have to show that you can still meaningfully construct these pairings. I mean, the way that Kate has constructed these pairings, at least in her recent preprint, is very concretely, just directly through formal extension of scalars on divisors on the curve. So you would need to mimic those constructions first in some way on your genus 2 curves. And I'm honestly not sure how you might go about doing that. But
is that true? Like the Tet pairing is actually can be defined over general Abelian variety, right? Or
yeah, you can define them in terms of more generally, certainly, right? I think any principally polarized abelian variety, right, will have a Tate pairing. So I think it's not unreasonable to hope that you could define these sesquilinear pairings on higher genus curves. But I'm just not sure.
I see.
How exactly you do that.
Yeah, I'll jump in. I'll jump in and say that I think that I don't see any obstruction to doing the construction in my paper for abelian varieties in general.
I see. Thanks.
So maybe I could also ask another question. So you said that like this sesquilinear pairing is a very like natural extension of the Tate pairing, but is there like a map from this like is there a natural surjection somehow or like a map from the Kate pairing to the Tate pairing, if you will?
Yeah, and I mean in a sense, like, well, maybe I'm not answering your question exactly, right? But we saw, maybe I can go back to these slides. How far back I have to go. Here. We can see how one can think about the sesquilinear pairing as, a very slight generalization of the Tate pairing. Right? I mean, these are all just Tate-Lichtenbaum pairings. This curve we've assumed to have CM, so this action by minus tau on P is no longer purely formal, right? That's just literally some point on the curve. Similarly for tau minus tau bar. So in that sense, I think if I'm answering your question, we can see how these pairings are products and tuples, say, of the Tate-Lichtenbaum pairing in disguise.
Okay,
it's yeah. I mean, one key difference, though, right? I should mention is that in general, right, you have sesquilinearity, right? So there is some twisting going on when you act on points by endomorphisms, and that, at times is a strict departure from how things work with the Tate pairing.
Yeah. Okay, thanks. There's also a question from Bruno in the chat. So he writes, speculative question. Do you think these sesquilinear pairings have further either constructive or destructive applications outside this class group attack? ?
I hope so. Triple question mark. No, I mean, that's a great question. I certainly hope so. At a minimum, and this is a fairly naive observation, but at a minimum, if we think about pairings as a sort of volume form, let's say on the M torsion, right? And if we take the spirit of recent attacks, such as the ones on SADH, to basically mean, if you know how the isogeny acts on M torsion for well-chosen M, you know the isogeny, that's not a result that's specific to the class group action problem. So if you have this new sort of volume form that is respecting not just C module, but O module structure, then presumably it could have applicability outside of the context of the vectorization problem, but I have not yet found them, but I'm sure they're out there, and I encourage you all to try to find them.
Maybe pushing that a bit further, like pairings have both been used constructively and destructively. I guess this paper sort of extends pairings to get better attacks, but could you see a constructive application where this could give you more than what like the tape pairing can? Because with the tape pairing, you can find ways to generate like rational two torsion point in like some more efficient ways. But could you see a constructive application where these pairings could give you like more tools constructively, or does it seem like it's more useful for cryptanalysis?
It's a great question, Maria. I think maybe I'm reflecting the bias of the field, but I've mostly been thinking about destructive applications. So I'm not sure, but I think it's definitely an interesting thing to consider. And again, one would hope that with the finer information provided by these pairings, you could do some of the things that you suggest. I think I saw something flit across my chat for just a second, but then I missed it.
Yeah, there's also a comment by Krein. He says that certainly the non-degeneracy allows you to say something about the image of your orientation in terms of its kernel, to use it constructively. Then he forgot to close the parentheses.
So we'll interpret that as an ellipsis.
Yeah. Yeah. Thank you very much. Are there any further questions? If not, thank you again for a great talk, Joseph.
Thank you.
Thank you all.
Sorry. In 2 weeks, we'll have Joella giving a talk, and it's also going to be quite related to some of the stuff you talked about now, about the generalized class group actions on oriented curves with level structure. So be sure to stay tuned for that. Otherwise, yeah, see you all in 2 weeks.
Bye bye, everyone.